Hi, I'm John Bin Lian. I'm a second year PhD student in Boulder Aerospace Engineering Department. I work with Tomoko. We focus on atmospheric electrodynamics and data assimilation. First, I want to thank all courses common and providing modeling data, and also thank the team of Chomp and Supermac teams for providing the data. Today, I'm going to talk about the comparison of observed equatorial magnetic perturbation of Chomp and Supermac with the simulated result of the TIE GCN on March 11 to 17, 2009, a case study. There are several contributions to magnetic field in our Earth. Depends on different altitude and depth. The first type is internal sources. Basically, we refer core and across the field as the internal sources. The second type is external sources, which result from the atmospheric current and the ring current and the current on the magnetopoles and the magnetotail. The last one is externally induced field. The induced current by the external sources and flow in the ocean and the Earth's interior. We call it externally induced field. In this study, we focus on atmospheric current. In the atmosphere, when the mixing gas moving with the neutral wind velocity, the differences in the neutral to ion collision frequency and neutral to electron collision frequency produce the charge separation and the electric field. The electric field generates the eastward electric current at the E-region altitude. If we look at the plane of the altitude against the longitude, here is the east, there is a west direction. The eastward electric current induces the southward magnetic perturbation during the daytime above the electric current. And on the ground, there's the northward induced magnetic perturbation we can observe in the ground space station observation. And basically, we can find the current in the night side is much weaker than the current during the daytime. For modeling the upper atmosphere, we utilize TIE GCM model. There are two sort of boundary conditions to drive the model. One is the regular one, GSWN. The other one is MERA time GCM at the 97 kilometers altitude. MERA is a modern era retrospective analysis for research and application. The data assimilation output from the lower atmosphere model. Time GCN includes the mesospheric dynamics. And using this lower boundary condition, the TIGCN can produce the stronger day-to-day and the longitudinal variability in comparison with the GSWN-driven TIGCN. For modeling atmospheric current and the associated magnetic perturbations, we utilize the 3D dynamo code. This model considers the three-dimensional current conservation at each grid point, and the model assumes a perfect conductor at the ground to depth 600 kilometers. And here is the condition for the GSWN case and the MERA cases. The same part are the model date. We simulate a week of model output from March 11 to March 17, 2009, so the minimum condition. The aurora forcing is from the MGEO assimilative mapping of geospace observations. The only different part is the low boundary condition. One is the GSWN, the other one is MERA-driven time GCM at 97 kilometers altitude. Later, I will call it as the GSWN case, and this one refers to MERA case. For the observation, we plot the CHAMP data charging mainly satellite payload. In 2009 March, the satellite was at the 325 kilometers altitude. This is the altitude we utilize to interpolate our model result. For the ionospheric magnetic field, can be approximated by this equation. The CHAMP data subtracted by the magnetic fields results from the core, lithosphere, and magnetosphere. The three magnetic fields are from the empirical chaos model. And here is the result. Since the chaos model was fitted under the quiet time conditions. So we apply this condition to plot the day of year 17 data. The right figure is the result of the ionospheric magnetic field in the geographic northward component in nanotesla, which is a function of the quasi-dipole latitude. And the red color is the observation. The blue color is the model result at the midnight in this subplot. So the spread of these curves shows the longitudinal variability under the same quasi-dipole latitude. During the dayside, the MERA case shows the stronger longitudinal variability in the off-equator region. At the magnetic equator region, the model performs the little bit weaker amplitude of the ionospheric magnetic field. In the GSWN case, you can see at the magnetic equator region, the model performs the larger amplitude for the ionospheric current and the small and weaker longitudinal variability in the off-equator region in comparison with the MERA case. So the two figures tells us the MERA case has the capability of modeling longitudinal variability at off-equator region. The second observation is the Supermac. And here is an example. We plot the result at this station in South America. The top panel is the DST index. And the middle panel, the blue color, shows the Supermac data in the horizontal component. And the red color is the fitted baseline. We utilize the Julian days and the DST number and the midnight data to fit the baseline. By subtracting the baseline, we can get the bottom panel figures, the corrected component in the horizontal component. So in this figure, we can see during the midnight, there's almost no current in this area. And here is the model data comparison in the geographic northward component in a unit of nanotesla, which is a function of local time. And the red color is the Supermac observation. The blue color shows the mirror case model result. In this case, the model shows the weaker ionospheric magnetic field during the dayside ionosphere than the observation. And there's a little bit phase shift of the peak of the two uh, ionospheric signal. The spray in this figure shows the day-to-day variability during this week. In the Geospace case, we can see the model performs the stronger peak of the ionospheric magnetic field, but there's almost no day-to-day variability in the Geospace case. And here is the model data comparison at the dayside magnetic equator. We compute the model to data ratio for Supermac and the CHOMP data, and plot the ratio where the CHOMP is near to the Supermac station. The distance is less than 600 kilometers, which is approximated by the model resolution and the length per degree and the altitude of the satellite. So here is the result model to data ratio in the percentage during the noon. And there's only 3 points for the MERA and the GS11 case, but using this approach, we can compare the model data comparison during the quiet time and to investigate the effect of the induced current at the ground. Since the induced current in a lithosphere, the direction is upside to ionospheric current. And our Earth, the lithosphere, is a good conductor. But in our model, the model assumes a perfect conductor in the lithosphere. So in our modeling result, that could show the stronger induced current in the model result than the actual current flow in the lithosphere, such that reduce the modeling magnetic field associated with the ionospheric currents on the ground. And here is the summary. The model performs the potential capability of modeling longitudinal variability of magnetic perturbation in off-equator latitude when we impose the stronger tidal variability from the atmosphere. And we need more model data comparison during the quiet time to investigate the effect of the induced current at the ground. And here's the reference. Thank you.